Yeah, welcome to this week's SPCL Bcast. I'm super happy that we could convince Sunita to join us today and give a talk about her recent work. And then I'll, without further ado, give it to Nikolai to introduce her.
Okay, thank you, Torsten, and thank you again, Sunita, for agreeing to give this talk. Sunita is an assistant professor with the Department of Computer and Information Sciences at the University of Delaware, USA. She got her PhD from Nanyang Technological University in Singapore. She's won numerous awards, most notably the 2016 IEEE CS TCHPC Award for Excellence for Early Career Researchers. And without further ado, we'll let Sunita talk about her excellent research. Thank you.
Thank you very much, Nikolai, Torsten, and team for inviting me to give this talk in your group. And thanks to everybody who has joined with us online. I see a lot of familiar names. Thank you very much. So so this talk basically is going to consist of experiences that me and my team has gotten over the past year and a half, trying to get this big plasma physics code moved from one platform to another. So we'll see how that goes, and I will look forward to questions later on. So moving forward, so to those who have not been to Delaware, which I would imagine mostly all of you, I just wanted to tell you where is Delaware situated. So the US map, it's in the far east, mid-Atlantic, so it's a tiny little drop. But we're nicely, bordered along with Washington, DC, Maryland, Philadelphia, a little bit New Jersey to your other side and New York. So nicely situated, easy to get to NSF, kind of organizations with just a train ride. And yes, we do use trains. So that's where we are. A quick shout out to my research group. There are about 6 PhD students and a few master's students and a handful of undergraduate students. I really like involving undergraduate students up front. So they get involved, in research projects, and they work in pairs with the grad students. So they get a, glimpse of what research is. And by working together with grad students, they also kind of get an idea of what grad school could look like once they get their undergraduate degrees. Also, many thanks to all the funding organizations that's been helping my group up and running, and lots of cool research along the way. So so loaded slide, but the main point here is the application of interest that is driving the whole research and development that we will look into this hour is PIConGPU. Where PIC is plasma in cell, so PIConGPU, and there is a bunch of people involved from HCDR Germany, so Michael Bussmann, Guido Jutland, Alex Debut, Rene Verdeira, etc. from the HCDR plus CASUS. The project is also funded by CASUS Germany, so thank you to CASUS Center for funding my PhD student, Matt Leinhauser. Most of the results that we'll talk about are based off of the results that we got out of Matt's research. There's also Georgia Tech and of course Oak Ridge National Lab, and I'll tell you in a minute why. Axel from Lawrence Berkeley, and so that's a big group. And thank you to Oak Ridge National Lab. Center of Excellence COE here is the AMD HPE team that is working with us to move this big plasma physics code to their next upcoming system. And also thank you to JSC for Jewel's booster module that we have used for some of the results. Hope I covered all of them. All right, so the program itself is called CAR, Center for Accelerated Application Readiness. That's what CAR stands for. The idea here is Oak Ridge National Lab has, I could say, recruited 8 teams across the United States to play with applications of our interest and find out, what does it take to move these applications from existing systems to the next upcoming system, which would be the first exascale system called Frontier. Frontier is being built as we speak at the Oak Ridge National Lab. So PIConGPU is one of the 8 applications belonging to the CAR program at Oak Ridge National Lab, where the idea is to move PIConGPU from current systems to Frontier. PIConGPU has already been running on Summit. It's run on Titan. It was the Gordon Bell runner, one of the teams back in 2012, 2013. And the idea here is X speed up on Summit, and the goal is to get 4X on Frontier. So what does it take? What is a path, right, from Summit to Frontier, but get that 4X speed up? So what is going to take us to get that 4X factor? The best part of working with domain scientists is you get cool pictures, cool images. So what you see on the left-hand side is, PIConGPU. It's a video, so I took a snapshot of, one of the still images. And this is, the credit goes to Felix Meyer, Richard Posch from HCDR Germany. And this is depicting one of the science cases of PIConGPU called LWFA, Laser Wakefield Force Acceleration Simulation Video. And this is using about 48 Volta 100, so 6 of Summit nodes with Isaac plugin to visualize, the code, 1.5 version. So we time and again get these videos from the team, and we put it out there, just to visualize what exactly PIConGPU is all about, and it's pretty phenomenal. Frontier in a nutshell, and I think I have another slide coming up. Whatever is information out there, public knowledge is what this contains as well. EPIC CPU plus Radeon Instinct GPUs from AMD, and the expected peak performance is 1.5 exaflops on Frontier. Right, a little bit more info that you would, totally get if you look up Frontier Oak Ridge National Lab online. EPIC CPU, AMD Radeon Instinct GPU, AMD Infinity Fabric, and which is a CPU to GPU interconnect, and the system interconnect is multiple Slingshot. And I would imagine, more information is going to come up as and when we get through the next few months, because Frontier supercomputer is expected to go live around the end of the year. I would imagine supercomputing, but that's the time frame. Okay, so I think the next few slides, I'm going to walk you through PIConGPU. So what the application is all about, and how do we look into the different challenges. Now, prior to me playing this video, this would be fun to do in person. I want all of us to close our eyes for 10 seconds, okay? Because I'm going to draw an analogy to better explain PIConGPU video from a computer scientist standpoint. So close your eyes for 10 seconds, relax. Imagine you're sitting by a beach. Imagine you have a cocktail in your hand. Now imagine there is a boat cruising through the water, forming waves, right? There is water oscillation happening. Now imagine there are surfers jumping into this wave, and they're getting accelerated because they are riding with the wave. And imagine this whole picture, right? So wonderful, beautiful picture, sunny day by the beach, boat cruising, water oscillation, a lot of waves, the surfers jumping into the wave, and the surfers are riding with the wave. Okay, that's a fun part. Now you can open your eyes. So that's the analogy. Okay, so now let's play the video. So what you're going to see here is a plasma chamber, which is basically the beach, the water, right? And you're going to see a laser pulse, which is going to tear through the plasma chamber, which is your boat cruising through the water. So this laser pulse is displacing electrons in this plasma channel or the chamber, creating a wake. It's going to create positive, negative charged regions, which is accelerating the electrons to get these higher and higher energy particles. And we're talking about giga electron volt, tera electron volt, and so on, with the goal to create this high energy particle accelerator. That's the goal of this PIConGPU project itself. And how do we create fast simulations? How do we create this high energy particle simulator, and how do we understand what's happening when there is this laser pulse tearing through this plasma chamber and creating that high energy? So that's what the deal is about. And I hope I got that across with my computer science hat on, and hats off to the HCDR team for explaining to me what PIConGPU is all about. Okay. So the basic understanding of PIConGPU, where exactly is this could be used, right? Compact X-ray sources of high brightness where you need higher and higher energy electron volts. So the idea could be going towards tera electron volt, but it's complicated. It's a challenge to get that far. And the other options could be for radiation therapy for cancer treatments, and particle and dense matter and stuff like that. So real world applications are quite a bunch when we have been able to create that fast and predictive simulation to build that next generation laser plasma accelerator. So some more visualization here. On the left-hand side, you see another image, and the credit here goes to Benjamin Hernandez from Oak Ridge Lab. It's another laser wake field, the thing that we saw in the other video, a simulation, also using Summit nodes, about 2 billion particles. It's again a still image, and using OLCF's cloud environment and ISAC plugin. So if you can imagine 50,000 to 60,000 lines of plasma physics code that's running on a Summit kind of a platform, which is currently the world's fastest supercomputer with IBM Power 9 and NVIDIA GPUs. Now we have Frontier, which will have AMD CPUs and GPUs. So it's not apples to apples, right? There's going to be a fundamental shift to how the CPUs and GPUs are constructed and what the fundamental architecture characteristics are. So to that end, we do not want to compromise on portability, of course, because you don't want to just run the code only on Frontier. It should be able to run on multiple systems. And by enabling portability, you don't want to lose performance. So portable performance or performance portability is a tricky phrase, and typically it's wise to not use them together. But that's where we want to head to, right? We want to achieve performance. We don't want to lose portability. And scalability, of course. So you want to be able to scale across X number of nodes that will be available on Frontier and other systems. Plus, this PIConGPU team particularly also cares about visualization, as you have seen just one video so far, and you've seen a couple of images. It's important to visualize, what the plasma is, how the laser pulse is interacting in the plasma channel, and it only gives you a very nice angle to the entire application when you start visualizing, what exactly is happening. So that's the other piece as well, which is of great importance to us. Going forward, the software stack for PIConGPU is predominantly Alpaca. Alpaca has been developed within the HCDR team over the past several years. There is some citations in the footnote if you want to look closer into the Alpaca software stack itself. But the main idea here is Alpaca is able to target multiple backends. So here we have CPU plus GPU backends, and which includes, AMD, NVIDIA, HIP. Of course, AMD's. I'm trying to move the Zoom box a little bit because it's hiding portions of my slide. Anyhow, so AMD, NVIDIA target, then HIP and CUDA, openMP offload as well, openMP threading plus openMP offload. It's got a SYCL backend too, as well as OpenACC backends. So the code prior to using Alpaca was over 80,000 lines of code. And with Alpaca, they've been able to trickle it down, a little bit to 50,000 lines by, creating those wrappers and making it more compact. And Alpaca is also being updated as and when there are more hardware and low-level, libraries, backends available. And I'll show you in a little bit. So it's a C++ 14 header-only library, and the idea is obviously to enable performance as well as portability. A reason why PIConGPU is able to run on multiple platforms without needing to recode or reprogram from scratch. Jan 2021, there was a new release. Again, that it's open source. So if you want to use it, if you want to create a PR and give us feedback, most welcome. And it's the new release adds compatibility to the latest CUDA releases. Mostly the new release was adding features of offload, OpenMP 5 specification features, plus OpenACC. The version you will see supports HIP 3.5 and onwards. There's more latest versions. A recommendation is to use it with the latest HIP version. And like I said, it's open source as well. Okay, so that's the software stack. I should also mention that we have multiple versions of PIConGPU going on. One is Alpaca, the other version is openMP offload version of PIConGPU that the SPEC HPG consortium, the non-profit organization, cares more about because, you know, directive-based programming model. There is also an OpenACC PIConGPU version. So I would say Alpaca, openMP, OpenACC are three independent versions going on, but Alpaca obviously has multiple backends as well. So depending on, you know, whom we have to talk to, we would use different versions. Plus, it also helps us, you know, work with the compiler developers and give them compiler bugs and runtime bugs that we would encounter as and when we use newer and newer versions of the compilers. Okay, so with respect to CAR program, that's the Oak Ridge program I was telling you about, the metric that we care is called the FORM, figure of merit, where we need a particular metric to say that we want 4x of that number, right? So that is particularly the FORM metric. So if you hear me say FORM case study, I mean figure of merit, and it's calculated by, you know, total number of particle updates per second, 90% plus the number of cell updates per second run over a period of time, a number of iterations. Yeah, so that's what the FORM run is. And PIConGPU has multiple science case studies. So we use a particular case study called TWEAC, TWEAC, for the FORM run. So you could have laser wake field, you could have Weibull instability. So there could be multiple case studies, you know, and FORM run TWEAC case study is the one that we care about for the CAR program particularly. The experimental setup that we have used for all the results that we will, you know, look into for the rest of the slide deck involves multiple architectures. Of course, there is Summit at the Oak Ridge National Lab. There is another system called Poplar, which is the early access system to Frontier. I believe we could call it a baby Frontier, but there is going to be even early another system prior to Frontier. So Poplar is not the early system. There's a next system that is also coming up as we speak. But the Poplar system itself has multiple nodes consisting of V100, MI60 of AMD GPUs, MI100 AMD GPUs, and of course AMD CPUs. Very recently, thanks to Bernd, we got access to Jewels. So that gives us access to A100s from JSC, AMD EPYC plus NVIDIA A100 GPUs. The software stack is the latest Alpaca 0.6.0 with those multiple backends. CUDA is predominantly 11.0, maybe 11.1 in certain instances, but mostly 11.0. AMD ROCm, that's of supreme importance to us because we are trying to build the code for AMD Frontier system. So we got to make sure that, you know, Alpaca is compatible with the ROCm versions and bugs and, you know, whatever we have, we keep reporting. And multiple versions over the past, since September 2019, when the CAR program kicked in, we've been using the various versions of ROCm and HIP that's been existing since then. The very latest one is 4.1.1, or yeah, I believe that's what we have used for at least this deck of slides. OpenMP offload compilers and OpenACC, but these are, I don't have much results or any results for offload compilers and OpenACC because the code has to build, compile, and execute first in order to get results. So that's where we are, and it's work in progress. Right, so most of the results here are going to discuss a little deeper into the profiling and performance analysis of the code using different types of tools. For any code, the fundamental thing to do, the very first thing to do would be to profile the code, right? In order to find out what the hotspots are, what are the compute intensive portions of the code are. Especially when you have a massive code base. 50,000 lines of code is still, decent enough, but you have sometimes millions to millions of lines of code. But before you probe into it, you want to know what is your compute-intensive hotspot. So first up, we do profiling. We try to identify those key kernels that we're interested in. And you could do that in several different ways. So I listed all the tools here that came to mind, and not all of them are profiling per se. They are profiling plus performance analysis. NVIDIA's NVProf, Insight Compute, Insight Systems, AMD's RockProf, which we have been playing a lot with. Of course, it is CRAPAT tool as well, and HPC Toolkit, Tau/Paratools, if you like, ScorePeef, Ampere, Liquid PAPI, or something that Liquid basically is something that we're starting to look into. Then you have Intel's vTune, ARM tools, etc. So to cherry pick the tools that we will see for this particular talk, it's mostly NVIDIA's tools and AMD's RockProf metrics. The benchmarks we have used to get those ceiling, right? What's the memory bandwidth? What's the peak compute performance you could achieve? We have used GPU MemBench and BabelStream, and if you're interested, there are references in the footnote of where these are. So these would give you pointers to the different pieces of the architecture, depending on what you're really looking for. So we used NVIDIA's Insight Systems tool to get a visualization timeline of the kernel. So like I said, PIConGPU could have different case studies, right? And we have been so far working on 3 case studies: tweak, LWFA, and Weibull instability. Mostly we're going to talk about tweak because that's the case study we have used for the metric figure of merit form run. But all these case studies have a couple of kernels that stand out. So those kernels are move and mark and compute current. So throughout the next several slides, if you hear me saying compute current and move and mark, these are the main important kernels of PIConGPU case studies, among few others, but these are the ones standing out. The blue, Pi compute current, the orange one is move and mark, and you have shift particles, and you have, the other, the gray the yellow piece, which is the others. The 75% of the overall runtime of the science case is dominated by these 2 kernels, move and mark and compute current. One more thing I wanted to introduce before we really look into the characteristics of the application itself is the roofline model. I guess we all would know what roofline model is, and we have been very closely referring to Sam Williams and Nanding's papers on roofline model, along with the one that's cited here, to understand what roofline models could really give us. And the right-hand side is just a cartoon of what roofline model is. Basically, it gives you a ceiling of how far you could go how far application could go based on memory bandwidth, and how far you could go with peak performance. So so here it's a visualization tool, and it could give you performance modeling, indicating the ceiling, hardware limitations, as well as depending on the different optimizations that you would introduce to your application. You could have several parallel lines to your diagonal slanting line, and you could have several parallel lines to your flat line, right? Suppose you're introducing thread level parallelism, data level parallelism, instruction level parallelism. You would draw those as parallel lines to your flat line here, because you're saying that to reach the peak, these are the parallelism that you would exploit in your application and in your hardware to reach that peak. Similarly, imagine L1, L2 caches, or high bandwidth memory, or main memory cache, main memory, and software prefetching could be some of your memory-based optimizations that you would do in parallel to your diagonal slanting line to say how far are you to reach that peak memory. X-axis, Y-axis. X-axis is operational intensity, flops per byte. There is a little thing there where different tools could give you different things. NVIDIA gives you instructions per transaction. AMD's RockProf gives you instructions per byte. So these are a few little intricacies that we deciphered during the process of exploring roofline modeling based on different architectures. Right, so another thing that a colleague was recently mentioning is roofline models can also be dominated by programming models, because different programming models could technically give you different types of optimizations, right? What CUDA could give you is not what a directive-based model could entirely give you. So depending on what you're using to program your application, you could go as close to what the peak is. So that's another factor. All right, so stepping through, this is the screenshot. So what I'm going to tell you is how we walked through using the different roofline models for both architectures and what the tools could give us, what the tools didn't give us, so how we plotted manually, and the things that we got automatically, right? And this is our way to communicate to the Center of Excellence, which is the AMD Cray HPE vendors, like, hey, look, these are the things, counters that we need to be able to visualize what's happening in the application. So this particular thing is automatically generated with Nsight, which didn't happen until we used NVProf. So Nsight could give us more automated plots, if you like. So this is particularly the move and mark kernel. And this is basically showing you speed of light, which you see in your x-axis, how close the kernel could get to running to the maximum throughput. Streaming multiprocessor utilization versus memory utilization. So that's what this picture talks about. And feel free to drop me an email later on, or I can point you to some of the reports that we have written for PIConGPU. And there is a citation in the bottom, which will take you to the osti.gov website, which is a report. It's a documentation of using PIConGPU and NVIDIA's tool. So it's public. You'll get a PDF. The second plot, this is a lot going on. I will walk you through it, so don't worry about it. This is Nsight Compute Tool, right? So this is an automated plot that you get from NVIDIA's Nsight. You don't get this when you use NVProf. So when we used NVProf all of 2019 until mid-2020, and we did hand-drawn roofline plots. By the end of 2020, there was Nsight Compute available, so we could match up what we got manually and what we got automatically. So the top plot is single precision. The bottom one is double precision. You see little circles here. So the purple one denotes L1. The orange one is L2. The red one is flops measurement. Your x-axis is arithmetic intensity, so flops per byte, and your y-axis is performance. Okay, so this is single precision, this is double precision, and this is move and mark kernel of PIConGPU Nsight tool. So what you really see here is the single precision is quite compute bound. You have all the three little dots hugging closer to your compute bound roof. And you are also seeing it almost close to your ceiling, which is good because it's trying to exploit the maximum performance out there. So the circles are where it could possibly be. The double precision is a little interesting, where you see the purple, the orange, as well as the red dots, hovering closer to the memory bound lines that you see. The good part about Nsight is you're getting these measurements for L1, L2, and HBM, which is not natural when you use another tool like RockProf or something. So this is a feedback that we give to AMD saying, hey, could we get something like this? So this has been part of the CAR program, right? What do you get from the tools, what you don't get from the tools, and how do you let the COE know that you need these extra counters? So the second plot is basically L1, you see, is the purple one, which is a little more compute bound, and lower instruction intensity makes your memory access pattern also strided, but you go after the arithmetic intensity, higher arithmetic intensity, your memory access patterns are not really strided. So it depends, how your kernel are. It could be compute bound or memory bound. So here we are seeing L1 is more compute bound, and L2, which is your orange, and the red one, which is the flops, are more on the memory bound side of things. So how would you work with the move and mark kernel? How would you create those memory optimizations to make the best out of the given hardware with respect to double precision? So that's on the table to explore further. And this is also part of that osti.gov report. So definitely take a look at it if you're more interested, because it's much more explained in length. So something else that we wanted to corroborate, because the previous one you saw was a roofline model, something else that you could create is instruction roofline plot. So performance roofline plot, instruction roofline plot. Instruction roofline plot gives you stuff like this: L1, L2, HBM, slapped on the same thing, and you could query all these with respect to NVIDIA metrics and then you could see these green stuff that's appearing, how far to your left, how far to your right, making your kernel memory bound and or compute bound. So this kind of a plot you don't naturally get out of a normal roofline model. So we went with the instruction roofline plot, again, basing off of Sam and Nanding's instruction roofline paper. So the other fun thing that I wanted to show on the screen in case there are students on the call. So this is something we really had a lot of fun with, again, on Summit. So this is the jsrun visualizer. And I mentioned students because I was told that this is work of an intern over the summer period who created a visualization tool for Summit with respect to the jsrun job script. So basically you see how the job script, for example, you see that little jsrun script, X number of processes, X number of GPUs used, that gets color coded onto the node, and then you see what part of the node was really used to execute your kernel. And we found it very intuitive. And when I was teaching this as part of my architecture class, I could tell them that, look, this is your node of GPU Summit. For example, 2 sockets, 3 GPUs per socket. So 6 V100s, that's what the 0, 1 through 5 is. And if you count this 7 rows, 3 columns, these are 21 cores, another 21 cores, 42, plus there are 2 extra cores for operating system, I believe. And so in total, you'll get a 168 total cores, and those are those light boxes in the background that you see because of hyperthreading. So when you give your job script, it nicely arranges in this visualizer and tells you how the job is being slapped onto the node. It just gives you nice extra info. So I just wanted to do an FYI. And if you click on the link, on the top, or just look up jsrun visualizer, you get access to this online tool. Okay, so we are still on Summit, and I'm going to show you a little bit about the poplars as well. So I'm going to slightly go a little faster. So this is the strong scaling run on Summit, again, a form run, and this is from November 2019, so it's a little older, but that's when we were able to pause Summit entirely, get exclusive access, and use full Summit to do a strong scaling as well as weak scaling of PIConGPU. So you see some dips, which was most likely because of MPI communication, which we still are investigating. But so much has changed that if we reran it, maybe we won't see those dips. And on the right-hand side, you see the different timestamps, different GPUs, the different total number of cells, particles, etc., used to calculate the figure of merit leading up to some X tera updates per second. That's a strong scaling, and similarly, there is a weak scaling plot as well, almost close to linear weak scaling. 10-minute run, 1,000 iterations. The time step per iteration is 0.6 seconds. That's also another focus point for us to bring it down to with Frontier. So how many seconds it took per iteration. The scaling is from 27 to 4,600 nodes, as you see. Again, this was done back in November 2019 when we had full access to Summit. And we haven't redone the plot anytime now, but we don't hope to see any massive changes. But this is our bar that we had to set to get that form metric and make sure that our future runs are aligned closer to this. So here you would see a plot, you see a table with Summit V100 as well as Jewels, because there is 800 results there. So we are looking at some execution time. Naturally, 800s are doing better, so it's not rocket science. But and the form case is newer form case since 2019, so there is a change to the algorithm, but the science case is still the science case. Execution time, obviously, lower the better. Giga instructions per second and instruction intensity, and this is using nSite, so it's instructions per transaction. Higher the better, right? So these numbers, higher the better, are good. Lower the better for execution time on Summit as well as Jewels 800. Okay, and this is for the form case study. Stepping through, so the takeaway mainly for the NVIDIA set of GPUs, where there's a bunch of numbers here, but bottom line is obviously 800 performed better, and we were able to achieve X percentage more with respect to peak theoretical flops. And obviously greater flops with respect to both single precision and double precision compared to Summit. We found kernels to be compute bound, some kernels to be memory bound, depending on single precision or double precision. Obviously, giga instructions per second increases when there's a faster runtime, and there is also instruction intensity increases when you have more instructions issued. So next, I think the more exciting part is the poplar, which is the AMD systems. So this is the one that is pre-Exascale system, I would say. And we have been using this over the past eight, nine months now and trying to move PIConGPU on it. So here is where the fun begins, because we need performance counters, right? And NVIDIA, as an established device and established tools, you already got them there. So by doing these analysis and studies, we go back to AMD and Cray and we tell them, hey, look, we need performance counters, we need tools. And we have come a long way. So hats off to the COE team for actually helping us get these measurements. So this one is based off of, again, Sam and Nan's instruction roofline model for GPU from PMDS 2019. We improvised that based on our back and forth conversations with AMD in order to get appropriate metrics for using RockProf and to query AMD's MI60 and MI100 GPUs. So here you would see a revised instruction roofline formula. What we care is the giga instructions per second achieved, giga instructions per second, the peak, as well as the instruction intensity, which you would calculate with a sum of bytes read plus bytes written into the execution time with the number of instructions by 64. Why 64? Because AMD has 64 threads and they call it one wavefront, as opposed to 32 threads being a warp with respect to an NVIDIA GPU. So warp versus wavefront, 32 versus 64. That makes it a difference with respect to these formula compared to NVIDIA as well as AMD. Then the other things we were looking into, which we did incorrectly for the first couple of rounds, were picking up these instruction counters from RockProf and trying to see what were available. So you have vector instruction counters, you have scalar instruction counters, and something else to keep in mind is there are 4 SIMD vector units per compute unit. So you would multiply one of the counters into 4, but there is only 1 scalar unit. So you will just multiply by 1. These are intricacies, but if you do it incorrectly, you're going to get funky numbers, which you don't want. So these were something that we had to do over a couple of iterations to get them right. So these are instruction roofline for AMD MI100 GPUs. If anybody is interested in MI60s, I can give you that offline. But the poplar system right now is more focused on MI100 because that's getting closer to what we want on Frontier. So here I deliberately used a plot that's giving us differences between the old tweak science case from 2019 to the new tweak science case, because as we use PIConGPU on these systems, what we are also realizing is because what the hardware can give us, we have the ability to improve the algorithm and push boundaries, which was a reason why we created a newer tweak, because it's better than the older tweak form runs that we got. So here you see 2 different colored points. Basically, this one is a move and mark kernel. This is the compute kernel. This is poplar using AMD MI100. And this is your HBM ceiling, and that's your theoretical peak ceiling. Note, this is giga instructions per second. And your little circle thing, not circle thing, I think it's a hexagon. That's an old tweak of HBM ceiling, and it's your new tweak of the HBM ceiling. And note that the x-axis is instruction intensity. Here it is instructions per byte, right? What we saw in the n-side compute was instructions per transaction. So you went back to AMD and we were like, can we get instructions per transaction? And they're working on it. Else we have to normalize and make those changes, and it's not quite straightforward. So yeah, so bottom line from this plot was we needed better performance counters, and even getting into the byte code could give us more information on how do you plot all this. Right, so if we want to look at more raw numbers and not just the plot, here is a comparison of the move and mark old tweak as well as the new tweak. So what you really see is execution time, giga instructions per second, instruction intensity. So we transformed the instructions per transaction into instruction per byte to make it uniform across the board. And this is old and new, right? So if you want to compare V100 across the board, we do see MI100 starting to perform better, and lesser execution time is definitely getting us more giga instructions per second. But with the new algorithm, with the new tweak, the execution time definitely reduced much better. And to that end, we got better giga instructions per second and a better instructions per byte. This is NA because right now poplar MI60 nodes are disabled because they want us to focus on MI100. So I would also do another takeaway here that as we were plotting these numbers, I believe the new tweak, the new algorithm was also the result of a reduced execution time. Definitely MI60 to MI100, there have been progress, but it also enabled us to come up with a better algorithm, which reduced further the tweak case, which is good. Very similarly, I'm not going into too much detail here, but the concept is the same with the compute kernel, right? Between V100 through MI100, better tweak is giving us lesser execution time, and compared to V100, MI100 is doing pretty well. So that's good news. So takeaways are the new tweak did show us some overall improvement. GIPS, giga instructions per second, instruction intensity per byte increased because of those following reasons, and these are all good things. What we didn't get with RockProf is the instructions per transaction plus L1, L2, and HBM measurements, which we could get from instruction roofline on NVIDIA GPU. So this is where we go back to AMD and ask them for counters, which they are working on. Right, so this is pretty much my, I think, last few slides. So I think we're good. So what I wanted to first mention is let us not quite compare A100 to MI100 because they are not similar. A100 is still a beast. So you should make sure that we compare apples to apples. Having said that, across the board, we did notice MI100 has the fastest execution time for both compute kernel as well as the move and mark kernel, two important kernels of PIConGPU. A100 naturally showed better flop performance over V100. The takeaways were need better performance counters, need counters to also measure flops on AMD GPUs, leave alone cache counters as well as main memory counters because they could get better. And we are told that they are working on it, so that's awesome. And the whole episode helped us push more science cases. So as I speak, the physics team in HCDR is trying to build more case studies because we know Frontier is definitely going to be way better than Poplar, right? So there is opportunity to get higher and higher numbers, enough to reach that 4x, which is the ball game between Summit and Frontier as per the CAR program. The most important factor in all this measurements and numbers was the rigorous testing of ROCm, HIP, openMP offload, AOMP, if you like, the AMD openMP compiler. But as part of the spec HPG work, because PIConGPU is one of the codes in the spec HPG benchmark suite that is being built as we speak. It's not released, so you may not be aware of it. It may come up later this year, but that's a different suite that is being built, and PIConGPU is part of it, where we have been compiling PIConGPU across all openMP offload compilers available, and that is helping the developers go back and find out what's the implementation, where are the implementation issues. So that there are fixes to be made. So I don't have numbers on that yet, but this Alpaca backend plus all this, roofline models and everything have helped us find out many issues and fixes in AMD MI60, MI100, and ROCm and HIP implementations, which is the main point of doing this CAR program. And I should give a massive shout out to the team, AMD HPE team, who we have been bugging over the past 18 months, trying to get PIConGPU running on Poplar and the next upcoming system. And they have been very patient with us and very nice to us, giving us lots of newer tools to use. And we have given them a lot of feedback. So the discussions have been wonderful. Everything is open source. This is the software stack, Alpaca, ISAC plugin, coupler. Everything is open source. GitHub is our to-go. And once again, thanks to everybody involved, and massive shout out to the HCDR team, sitting in Germany, who have been super instrumental, plus my student, Matt, who has, those are all his plots, basically. And he's literally a third year PhD student. So hats off to him too. That's pretty much my last slide. So thank you very much for listening.
Thank you, Sunita, for the excellent talk. Very interesting to hear about these challenges. Before we move to Q&A, just a quick advertisement for our next SPCL Bcast. The details will be up on the website soon, but on the 3rd of June, on this same time slot, 6 p.m. Zurich, noon Pacific time, we'll have Rob Schreiber and Natalia Vasilieva from Cerebras speaking.